Let's start. I will first share the screen, then I will unshare it if I remember.
Okay, I mean, it's there.
That's what they see, yeah?
That's what they see. Yes.
Okay. Okay, welcome to so this is next week we still have lectures, right?
One on Friday. That's it.
No Monday?
No.
Really?
Well, I mean, we have the exercise session on Wednesday, but that's it.
Why is there no lecture on Monday?
This is the lecture.
This is the lecture of Monday.
Yeah.
Correct. Okay. Okay, so next week we have only one lecture, and that lecture is on Friday, and it's going to be remote, and it's going to be just review. So I hope people will ask me questions. People are not very active in that respect, but if nobody asks any questions, then I will just make the questions myself. So last time we started how do you do that other way? No. There, okay, I can just click here. The last time we started talking about reinforcement learning. And today we go into the details somehow. Okay, so the details, let's start with the multi-armed bandit. I am now working on something called multi-agent, multi-armed bandit with some here. Okay, so this is the simplest possible framework to study reinforcement learning. There, it's a game. So the name comes from one-armed bandit. So you know, if you go to these kind of casino gaming places, there are these machines where you put a coin, and there it's called slot machine because there are these slots where you put your coin, and then this is what is it? Anyways, they're rotating discs, and if you get 3 in a row, you win. And in the past, nowadays you don't have the arm, but in the past they were mechanical, and there was like this thing that you have to push, and then it rotates, and then if you win, you get a lot of money, and it's kind of exciting. Okay. Now the multi-armed bandit is a mathematical generalization where you have many arms like that, and each one of them has an average return, like this one has. This has an average return, but it's not normally distributed. Usually these things have a distribution like that, where this is the average. Like here, like it's a very, you kind of win like a jackpot, then you lose most of the time. And the average is here, which is below 0. So don't play. But in this mathematical model, we actually have normal distributions. And so this has some average return, and it has some variance. And this has average return and the variance, etc. Each one has its own return and variance. Now, this is, by the way, not seen from Zoom.
I just
You
made
just
it
did
see,
it.
yes.
Okay. Is it better like that? Can they see the slides also from there?
Honestly, yeah, it can work.
It's not as good, but yeah, they can. Okay. Everyone said they can. No, somebody said. Okay, good.
Okay.
So, yeah. Good. So what is the strategy? Suppose you're playing this game and you don't know these means. You can start pulling these levers, these arms, and you can observe your return. And basically, you can collect the data set. You can collect the data sets, just like your return on step 1, step 2, 3, 4, etc. And you record, okay, so on the first step, I pulled arm 2, the arm 1 is 0, 1, 2, 3, okay. I pulled this arm and I got reward 5. The next round, I plugged this arm and I got reward -1. And then I plugged this, I got -2, 7, 6, 2, 2, etc. And then here you take, you look at the averages. So the next step is will be n+1. Before the next step, and here you have step n. Before you go to step n+1, you collect the averages, and suppose you have here some. Let's do know again. Sorry, it's probably not consistent with the book, but there's some average you collect from here, some average you collect from here, some average you collect from there, and some average you collect from there. Now, you might assume that if you played for a long time, and let's say you played all of the arms a lot, you can assume that this reflects the actual average of these arms. So maybe what you could do, you pick the highest one, whichever is the largest so far, and you just play that one. So that's a policy. So in this case, your policy from given all the history we ever done, you collapse it into averages, and whatever the data, you say take maximum, take the arm max, right? So it's like the arm which maximizes the average, whether it's 1, 0, 1, 2, or 3. What is the problem with this policy? The problem with this policy is that you always take the maximum, so you don't contribute to the collection of the data. So it very easily will happen that you try one arm and you have some prior average, like before you did anything, you assume that these are 0. So now when you played one arm, your data says this is the best arm because you won. So why don't you play the same arm? And then you always just play the same arm, and you never, with this policy, you never get to try the other arms. If you are lucky and your first move gives you negative reward, worse than you expected, Now you select one of the other arms because now it's not the best, so you play another one. As soon as you pick accidentally, like your average grows above some limit, you just stick with that arm and you stop exploring. And that can be bad even if you explored for 20 steps and you switch to this strategy, it might still be bad because even in 20 steps, your data might have been so noisy if these variances are large. You know, your data might show that this arm is the best, but actually this is better. It's just that you happen to be unlucky and like lucky with this arm and unlucky with that arm, and so you got better results, and so this strategy isn't good. So that's called exploitation strategy. Exploitation, because you exploit the knowledge that you have and you act on it. It can also be called greedy. Greedy because you are being greedy. You're taking whatever you think is the best at the moment. The other option is exploration. And exploration means that you select a completely random arm with equal probability. Even though your data shows that some arm is the best, you still just pick some random arm. And if you mix those two, then you are likely to actually both learn and win. So this is exploitation strategy. And exploration, let's call it phi prime, will be no matter what's the data, you just randomly sample with a uniform probability distribution, uniformly random. Okay. And then the actual strategy will be a mixture where basically, so phi star of the data will be phi the exploitation with probability one minus epsilon, because the other one, exploration, will be with probability epsilon. So usually the idea, why is it like that? Because usually you explore less than you exploit. You, let's say 1 in 10 moves, so with probability 0.1, you pick a random arm, but with probability 0.9, you follow this greedy strategy. But then you can analyze what will happen when you modify this epsilon. Make it higher or lower. If you make it 0, you never explore, then you get stuck somewhere. If you make it 1, then you never exploit, and you just randomly select an arm. So definitely suboptimal as well. But there is some optimal kind of value for this epsilon, probably. And depending on also several factors that you want to take into account. Okay, so here here we see, maybe I can zoom it even more. Here what we see is calculation of the average. So the R1, R2, etc., are the rewards that this player has received from arm A. And NTA is the number of times that this arm has been picked so far. And then you divide it by that number. So this is just really fair and square. The average, no weights, no nothing, just the average of the past performance. Okay, if you never pick that arm, then you have to assume some prior value, like I had 0 there. And when the number of times that you have selected this arm goes to infinity, you will eventually converge to the actual average by the law of large numbers, which is the special case of the central limit theorem, which we already had. The central limit theorem is stronger. It says something about the normal distribution. The law of large numbers just says that your average will converge to the average of the original distribution, not saying anything about the shape. Okay, so that's what I just said. Now, this is the book's notation for the greedy policy, right? So the argmax so take the arm which maximizes this cumulative average, and then we weaken it by saying here, do you see my cursor online? Oh yeah, of course you see, because you see my screen recorded from outside. So here is epsilon greedy, which means that with probability epsilon, you pick random, and then otherwise you pick the maximum, the best one. Okay, so here are, I can use a mouse. Oh. Okay. Okay, let's see. So here's an example. Greedy policy clearly gets stuck somewhere below what you could get there. So some arm would give you 1.5 or even larger reward, but with a green curve, which corresponds to no exploration, you get stuck. With a little bit exploration, you learn, but slowly, because only 1 in 100 moves, you actually explore. So you collect data very little, and so you get stuck to some non-optimal arms for some time, always, until you break out, and then you go up and up. I wonder why this curve is actually not a little bit like jumpy like that, because I would imagine you would get stuck at some arms, but yeah, interesting. You could simulate this in your own free time. I'm not going to give programming exercises in this course because that's like not the style of our course. But if you want to do this on your own, that's a nice exercise. And then when we explore a lot, 0.1, we learn faster, and we're actually, look, we're dominating this other curve all the time. Even at the end, I wonder if they ever converge. Yeah, they must eventually converge to the same thing. But after 1,000 moves, we're doing much better with the less greedy, more exploration, less exploitation. Okay, what is the difference between those? Just the same with percentage. Looks like better visualization. Um, all right. So obviously, if you do the programming, you do not have to keep in mind all that data. You don't have to store it because all you care about are those averages, and you can compute them. You can compute them here. The next step, the average of all the rewards so far. You can open it up like that, blah, 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 and you can see that you can express it in terms of the previous average, step K, and the new reward for that arm. So, and the K is the not the time step, but the time step picking that same arm. How many times I picked that same arm? So you only need to store the previous average, and from that, for each arm, and then when you pick that arm, you do this, and you get the new average. That's pretty neat. So that's the reduction of the state space. So the full state space, or like what we call in our research the history information space, will be consisting of all of that data, but you collapse it and minimize it, so to speak, in this case to just these four numbers. And so now your state space becomes like a 4-dimensional space in which you transition. Okay. Let's move on. That's about it. As you can see, you can do a lot of different theory, which we don't do. Okay, so back to this picture, which I drew not yesterday, on Tuesday. So in this case, the environment is this. The agent is whatever is your data structure, having those collecting the data, the state, the policy, and the policy outputs an action, does something to the environment. The environment goes to the next state. In this case, there is no environment is always in the same state. Then it outputs a reward, and the agent gets the reward and it gets the state, but very often you don't really observe the entire state of the world, but just some projection, some sensory data, which corresponds to the state. In the case of multi-armed bandit, there is nothing, the agent doesn't sense anything except for the reward. So the reward is all you got. Very often you also sense something else, like distance to the wall, some other parameters of the environment. And in this context, things are usually presented in terms of probability distributions. And in probability distributions, and there is an assumption, it's called Markov assumption. So let's, I guess I can remove this. Maybe I'll take a picture of this just in case. Less space for me today. So the environment is given by a probability distribution. We have a state and reward. So the environment outputs a state and the reward. The next state and the reward. So this S prime is whatever state is going to be next, given the current state and the action of the agent. This is the Markov assumption, or this idea includes the Markov assumption. The Markov assumption means that the next state of the environment depends on the previous state, but does not depend condition of the previous state on any other state in the past. So just like in physics, if you know the state of the world now, let's say classical mechanics, forget quantum mechanics. You know the state of the world now, you know the momentum of the particle, the speed, the acceleration, the mass, then you know its position in the next time step. You don't need to know where it was yesterday or 100 years ago. So that's the Markov assumption. Sometimes it's not true. Sometimes actually it does impact what happened yesterday. It might impact what is happening tomorrow. But in this context, we assume that it does. Then the policy is also a probability distribution, and it gives probability for a particular action given the previous reward and the previous state of the world. Now, if the agent does not sense the entire state, it has only some partial sensory data, you can still have this in this form. So this probability depends somehow on the previous state, maybe not just doesn't depend very precisely. Maybe for 10 different states, this probability is going to be the same. If the agent cannot sense the difference between them, for some other 10 states, it's going to be different, and so on, depending on what the agent can distinguish or not. And also the reward itself is a probability distribution, which, well, it's actually marginal from here, right? So maybe let's use a different letter. So this would be, you can compute this from this. So it's whatever are the possible next states. So you sum up over that, and this is the margin, it's called the marginal distribution. How many of you are familiar enough with probability stuff? We've heard marginal distribution. No? So well, let's look at it a little bit. So if we have a two-dimensional, so if a probability, what's the probability distribution? Let's take an example, the dice. Dice. Okay, so each dice has the same probability and 1/6. All of them the same. Now, if you throw two dice, you have a two-dimensional probability distribution. You cannot get one, but you can get 1 and 1. So that's here. That's 1 plus 1. It's 2. At the other extreme, you can get 6 and 6. And that's 12. And you can get all combinations in between. So you can have 3 and 4. That's 7. But you can get it also by having 4 and 3. also 7, and you can have 2 and 5, it's also 7. You got 1 and 6, there, also 7, and you can have reverse 5 and 2, and 6 and 1. It's also 7, etc. Right? So, and then here we have, let's say, 5, which you get from not 5, 9. So here you get it from, cannot get there. So 9 would be here. So that's from 5 and 4, or 4 and 5, etc. So actually you'll get those kind of lines of constants. Now this is a joint distribution. It's called joint distribution. And in this joint distribution, these numbers, these two variables are independent. So meaning, if you know what was the answer for one of the dice, you still know nothing about the value of the other dice. And you can see it from here very clearly, because if I fix one dice, then the other dice can be anything here, and the probability is the same. And then, okay, so the probability of each individual square is 1/36, because there are 36 different squares, and the probability of a single square is 36. So if I now want to calculate the probability distribution of my answers given one of the dice, so I fix that my dice is my other dice is value 4. I want to calculate the probabilities for the other dice. So what I do is I say how does it work? No, that's not what I'm calculating when I do marginal. This is not. This is the conditional. Okay, so this is the conditional distribution. If I say that I fix one dice and I kind of look at the slice here, which is going to be the same because they're independent, that's called the conditional distribution. Conditional, and it's denoted like this: probability of the second dice being something, just probability of the second dice being something, conditioned on the first dice being 4. And if you don't specify what it is, you can drop this as well. So you can just write like this. So this is the conditional probability of the second dice if you already know this the first dice. So this is the meaning of those. So the probability of next state and reward, assuming that you know the other state. And in case of dice, it's kind of boring because they're independent, so it's always the same. Now, the marginal distribution is the probability that the second dice is something, is, let's say, 4. Or let's say, pick a different one, that's 5. So what's the probability that the second dice is 5? Is a marginal probability that the second dice is 5, given that the first, I'm sorry. The probability that the second dice is 5, the same thing as the probability that the second dice is 5 conditioned on the first dice is 1 or 2 or 3 or 5 or 6. So we take the sum. So these are all the possible possibilities. So if I sum them up, I get the total probability that the second dies is 5. That's the marginal distribution. So, okay. Quick introduction to probability. Maybe it would be a better example of some dependent variables. What are dependent variables? What's a good example of dependent variables? Come on. Height and age. Not. Yes, okay. Height and age, they're dependent variable up until some point. Until
Then go the other way around. Go young, small, we grow up, and then we start getting old, we start small. Then go down.
right. Eventually you're horizontal. Okay. Yeah, it's good to laugh at those things when it's still far away. Okay.
Is the camera seat there?
Yeah, I
Okay.
can check if I can. So, okay, so let's look at height and age. So they are definitely dependent. And let's look at until 10 years. So we get like something like that, but actually it's like that, right? So it's the normal. It's for each fixed age, that slice is a normal distribution. That's the condition, but it's a different one every time. So if I have height given age, what I'm talking about is that when I specify the age, then what is the distribution of heights? If it's 1, then it's between something like 40 to 60 centimeters. Is the standard deviation. It's 10 and the average is 50. And then it goes up. Okay. Now, so if I have a child and I don't know what his or her age is, but I know it's between 0 and 10, what is the distribution then? It's none of those slices anymore. It's some sort of a combination of all of that. So if I don't know what the age, so I only look, what is the probability of just the height? Well, that's the marginal distribution. That's going to be, well, in this case, we'll take an integral because it's a continuous, but suppose suppose it's like year by year. So the year goes from 0 to 10. And you sum up those conditional distributions for that age. So for age 0, you look at the distribution. For age 1, for age 2, so you combine all of them, you get some normal distribution, which is common. The sum normally distributed variables is normal. So you get a normal distribution, which is somehow the average is somewhere in the middle and blah, blah, blah. So that is the marginal. And that's why we get back to our situation. Now that's why the reward, the next reward is computed from this as a marginal distribution, because you could have one reward if you go to, you go to a restaurant, so your next stage is some restaurant. It depends on your action, but it's also like some probability distribution. You go left, you go to Chinese or sushi. You go right, you go to an Indian or some soup place. Randomly somehow. Very hungry. And then you will have a reward in each of them. Someone is going to be very delicious and expensive, someone is we have different rewards. And now, given your current state and your action, you can compute the average reward. So if I go left, it's either the Chinese or the sushi. So I sum up, I take the average between those two rewards. I take the average. Should I divide this by something? I should multiply this by, well, this is just the probability. This is not the, it's actually not the average, it's the probability. Probability to get this reward. What's the probability of getting that reward? Probability of getting some other reward. So fix the reward. Let's say you go left, there are 3 different restaurants. Two actions, left, right. Here are 3 possible states where you can end up. And the rewards are given like this. And the probability that you get that to them are half, 0.2, 0.3. Same there. 0. As a reward, 0.1, 0.1, 0.2. And here you get with the probability, same probabilities. Now, if you go left, then with probability 0.2, you're here. But if you want to calculate the probability that your reward is 0.2, then you sum up the probabilities of going here or here, because these are both states for the same reward. So then it's 0.2 plus 0.3. So you go left, probability of getting reward 0.2 is the sum over these 2 states, S1 and S2. That we have this reward given that the state is S I. Okay, I goes from 1 to this case. So it's going to be 0.2 plus 0.3, so it's 0.5. What's the probability that if I go left, that my reward is going to be 0.1? Also 0.5. So my average reward, and I can compute, is going to be between those 0.15. If I go to the right side, my reward on average is less. So the optimal policy, at least for this one step, is to go left. Okay. Let's look at some examples. Oh, it's 5. Do you want to have a break or end our lecture earlier? Who wants to end the lecture earlier? 1, 2, 3, 4, 5, 6, 7. Who wants to keep a break? Yeah.
I'm okay with that.
You go with everything? Okay, so let's continue. Let's continue. Let's look at an example with a robot, page 69. Okay, so we have a robot and we have a very simple model. The battery of the robot is high. I'm sorry, I missed a question from the chat. Somebody asked something about the multi-armed bandit. The answer is yes. In this case, epsilon 0.1 was better than 0.01. Okay, so our robot can have high battery or low battery. If it has high battery, it can either search more, I don't know what it is searching for. Maybe it's cleaning robot, so it's searching for dust or some other dirt. Or it could wait, just stand and not move. If it's low battery, it has three options. It can still search, it can wait, and it can go and recharge. That's it. That's all the actions. Then there are certain probabilities about what will happen. If the battery is high, then with some probability, if the agent goes and searches, so it works. So then with some probability, the battery will go low. In this model, that probability is 1 minus alpha. Alpha is some number that imagine is 0.2 or something, or 0.7. And with probability alpha, it stays high. If it's waiting, then the battery stays the same. If its battery is already low and it goes searching, then with probability beta, the battery will stay low and it can continue operating. And with probability 1 minus beta, the battery will go empty and the agent will crash, like very bad. So how do we model very bad? We say it gets reward -3. So in the world of that agent, that's a very bad penalty. Some human has to come and pick it up. Let's look at this table. It should clarify our notation. So these are all possible combinations of the current state, the next state, and the action. Okay, so if transitioning from high state to high state with search action is probability alpha. Transitioning from high to low with searching is the opposite, so it's the complement of alpha, 1 minus alpha. going from low to high means that the agent's battery got empty, a human being rescued it and put it to charge, and then it charged up. That's why it went from low to high. But in this case, the agent has to pay a price, gets reward -3. So should avoid it probably. Gets from low to low with probability beta. And then if it's waiting, then it always stays at the same battery level. So it's not wasting any battery when it's waiting. So from high to high, probability 1, from low to low, probability 1, and probability 0 that the level of the battery will change with the waiting action. And then if you go to recharge, again, you certainly will go from low to high, and from low to low you cannot go if you recharge, and from high to low you cannot go if you recharge. Why is it not even part of this table? Who is
So because it probabilities, like
yeah, cannot happen. Why cannot happen?
it was not in the
Correct. It was not part of the actions that you can take. I think this is this is a very common assumption in robotics that there are some actions you can take, sometimes it's action you cannot take, but I think that's BS. The robot could always mistakenly go and charge. Why? Well, like there's some magnetic field around the charger that prevents it from going there, or what? But okay, this is standard assumption. It's somehow not part of its database or whatever, so it's not going to charge when the battery is high. Just not an option. That's why it's not part of this table. Okay, that's called MDP, Markov decision process. Markov because of the Markov property, and decision process because every time step you should decide based on this thing which action you select. So here is a graphic visualization of the same thing. 2 states only. So think about it. This is the simplest possible model you can imagine. Only 2 states, but it's already complicated. 2 states. Okay, so let's look at this. If you're low and you recharge, so the left number, the number on the left is always the probability of transition, and the other number is the reward. So if you recharge, okay, you don't get any reward, you don't lose any reward. It's just certainly with probability 1, you get your battery topped up. If you wait, again, then nothing will happen with probability 1. You get no reward, I guess. Oh, there are some rewards that were not specified. So waiting and searching give you some rewards that we don't know what they are. Yeah, let's, by the way, look at this notation a little bit. So this here is this marginal distribution. So this is the probability of the next state given the previous state and the action. And so here, for example, the next state is high if given that the previous state was high and the agent searched, and the probability for that is this. Okay. So here we can see if your battery is high and you search, now this arrow splits. You go back to high with probability alpha, and you get the reward for searching. And with probability complement of alpha, you go to your battery goes low, and you get the same reward because you search. If you're low and you search, so you take a risk, you might end up depleting the battery. So then you go, in that case, actually, what happens is that you get the reward -3, human being comes and picks you up or recharges, and you are back to high, or you go back to low and you get the reward. Then you can also recharge and go back here on your own, etc. Okay, so that's clear? Pretty much. Okay, now. So this is value function. I'm trying to get to the Bellman equation with you guys today, because that's the most important thing in reinforcement learning, I think. Okay, so what is, first of all, we need to talk about the discount factor. So we talked about it yesterday already a little bit. Take a picture of this. So at each time, we have something called G, which is value. Value would be the reward you get now. Yes. Reward you get now. So this is like projection into the future. Plus some gamma times reward you get in the next step, plus gamma squared times reward you get in the next step, etc. So that's the infinite sum one. Let's make it like this. Discounting the future. And the reason, and today I was talking to Steve. Steven is our Laval's professor. Said, it's a nice explanation. He said that, yeah, you discount your future rewards because they're uncertain or something. He said the reason they introduced it is because that's how the series converges. So it works mathematically. That's it. That's the reason. Okay. Okay. Now, what we want to estimate this. So estimating this means that we take the expected, maybe I don't need this. So what's the expected value of this G? It is the expected value of this thing. Moreover, if I condition it on the state where I am currently, and how do I get the next rewards? It depends on my policy, right? So that's why we have here policy there and the current state here. So if I know my current state and I know what my policy is, then everything else is determined. The average or the expected rewards into the future are all computable from this transition probability distribution and the policy and everything. So if I want to, okay, so and then this is denoted as values. Value of some policy given some state is the expected value for that policy of this G given S, and that is exactly what is there. Okay, I missed the +1, so actually you go from the next, you start computing it from the next state, not from the current state. So just add +1 here. It's consistent with the book. Okay, so that's the value. And at each point, and for given policy and every state, we can also refine it and ask what is the expected value of certain state and action. Because here we only look at what the current state, and then I apply this policy. Here I'm in this state, then I take that action, and only after that I apply this policy. Otherwise, it's the same thing. Okay, so then here's the cool thing, which is the consequence of the definition of the. So by the way, actually, this is the second benefit of defining the discount in this way. It's not only that it's convergence. Actually, I should tell this to Stephen. Let me share the screen now because this is important to see. I'm sharing this with the Zoom. Okay, so the value is the expected value of this G given the state. Okay, let's open it up. This is still the same as in the whiteboard, this part, or was in a whiteboard at least. Now, separate from here what is happening. We take the sum from 1 to infinity, and we take the first element of this sum outside. So the first element of this sum is k equals to 0. So this gamma is then, maybe I should do it. Let me do it. Explaining.
Maybe unshare then.
And then I should unshare. That's right. Okay, sorry guys, I'm unsharing. Back to the whiteboard. Okay, so we have expected value of this. Is this familiar? Familiar with this notation? That should be when I was in high school. It was nice. So. Okay, given that the current state is some S. Now let's focus on this. When K is 0, we can open up the sum one step. K goes from 1 to infinity, so it's over the first term outside. Okay, then I make an index trick. I replace, I shift all these K indexes backwards by 1. So I start from 0. So now because I start from 0 instead of 1, I have to add 1 to each of them. And then now I have gamma to the power K plus 1. Gamma to the power K plus 1 is the same as gamma times gamma to power K. So I take one of the gammas outside of the sum, goes here. That's how I get, and gamma to the power 0 is of course 1. So that's how I get this. And then what happens then? Then I'm simply writing what expected value is. What expected value is an for the first step. So I multiply by the probabilities of different actions. It's easiest to understand if I draw it. S. From S I can go to 3 different places. S prime 0, S prime 1, or S prime 2. So I'm basically pushing my calculation from this state to the successor states. The probability that I go to this place is given by the probability of, okay, first of all, I have different actions, right? So some action takes me there, some other action takes me there, and here maybe there's some action A2, which with probability half takes me here, probability half takes me there, etc. So when I fix my state and I fix the action that I do, then I have fixed the probability distribution of getting to one of those next states. And so I multiply by that probability whatever happens in that next state. So once I fix the action, now the environment transition function determines which of the next states I transition to. So this is why I'm summing up, and the reward doesn't really matter. So actually this would be replaced by taking the marginal distribution. So I could remove this, make it a little bit easier to read, but this means that I'm just taking the marginal distribution, and this means that I'm taking the average over the exact same thing. So here, what they do here is exactly what we already did. So this is the value function for the next states. And that's exactly what's happening in the next step. So I replace this whole thing with this, because instead of computing my value function at this state, I simply compute it in all of the next states and I weight it by the probabilities of getting to those states with my current policy. And so now I have a funny situation that I just reduced my calculation of my value at this state to calculating it at the next state. And you could think, well, so what's the point of that? So I just pushed the calculation one step further. But the reason is that now we obtained this what's called Bellman equation. The Bellman equation is exactly this. So it's like saying that that one is always equal to that one. And from this you can solve actually this V, because now you can express this V as a vector, like as all the value. You can list all the values of V for all the states. For example, if you have 20 states in your world, you can write the same equation for all of the 20 states, and now you have a linear equation where you have 20 variables and 20 equations, and actually you can solve the Bellman equation. So then you can actually get to this V, this value, from solving the Bellman equation. That might be a little bit overwhelming. I can understand that, but we can go through some examples soon. Yeah. Oh, right. We'll end early. Okay. Yeah, we'll go through the example. I just show you before we stop with the theory, the Bellman optimality equation. Same kind of derivation, but now instead of the expected value, we have a maximum. So we want the maximum possible value. We want to select an action which makes the value go up as much as possible. And in the similar way, we get this equation. So we assume we have some maximum value. So it must be the value of transitioning, selecting the maximum, the action that maximizes this value. And you do the same kind of trick, and you get an equation relating the maximum value at this point to the maximum value in all of the following points, or the next points. And actually, this operator, and by operator I now mean this entire thing here, that you basically apply to your V star, that happens to be something called contraction. It makes distances smaller because of this gamma. It's again another benefit, by the way, of having gamma smaller than 1. I should tell Steve there's other benefits. They're all mathematical, and none of them is really meaningful otherwise. Okay, because this gamma is less than 1, this operator reduces distances, and because it reduces distances, we can apply something called Banach fixed point theorem, and that's why we can prove mathematically that this equation has always a solution, which means that if you have a Markov decision process, there's always an optimal policy, and you can compute it with this optimal value function, which you get by solving this equation, and it always has a solution. Fine, but we are not going to be concerned with the optimality equation so much, but we will be concerned with the Bellman equation. So let's have an example. Let's have an example of this. Now I try to make an example which is not the same as the exercise. But let's have a super simple. Have two states. And two actions. Well, two states, two actions. S0, S1. And the transition. Okay, let's say the actions are left. Let's maybe it's okay, left and right are the actions. And if your current state is S1, and you perform the action to go left, then you go to S0, and you receive a reward 1 with probability 0.8. Okay, so it's a really good idea to go left from here, because if we go, okay, let's see what's the other option if we do the, if we're in the exact same situation. It could also be that we stay and we don't get any reward. Okay, so if I'm here and I try to go left, maybe it will succeed or maybe it will fail. There's no other options because this sum up to 1. If I'm in this state S1 and I try to go right, then I bump into a wall and I lose. So I stay in this, I don't lose, but I lose points. So I stay in the same thing. I get negative reward, and this happens always if I do this. Probability 1. And let's say it's exactly the same. No, not exactly the same. Let's say for S0, we have a simpler situation. And for S0, if we're in S0 and we do anything, both L or R, I always stay in the same place. And I don't get any reward. And this happens always. Okay? Sorry, no, that cannot be. That happens if I go left. Nothing will happen to me. I could be going left and I just stay. But if I go right, then I transition back to S1. But I don't get any reward. Okay, so okay, this is my model. So the idea that I have in my mind is that the best reward you get when you go from S1 to S0, but not the other way around. So if you want to collect a lot of reward, you should be going back and forth. Even though you don't get any reward here, even though you don't get any reward from going back, still you should go back because that's the only way that you can make this transition happen with probability 0.8 you actually get a reward. So the optimal policy is to from here to go here and from here to go there. So let's see how this works out with Bellman equation. So first we want to let's first compute the value for some policy. Okay, so let's suppose my policy is some stupid policies that I always go randomly. So this is the probability 50-50. My action, any state, so this could be L or R. For any state, always 50-50 probability. So let's compute the value of that. Now I think I really need more space, so I will. Can we switch off? Wait.
No.
Okay.
So there's
just
no
thinking.
convenient off button.
The thing is, maybe I should copy the.
And the blue is gonna disappear.
Okay, I'm going to copy the equation over here first. It's going to go off.
Sure. It works like in other rooms.
Okay, so here's our equation, and we're interested in the value. Let's take first the state S0. So what is the value of being in state S0 if my policy is random? So I write this out. So it's a sum where A is any action, L or left or right. Probability that I make my move to that one, but my probability is always 0.5, so I can just write this times my transition probability to one of the next states. So basically, there will be there will be two. So the transitions do not depend on the reward; they only depend on which state we are going to. Are we staying in S0? Or do we go to S1? And that actually completely is determined by so actually the reward is always 0 with probability 1. So if this R is not 0, then this is just 0 because it's 0 probability to have any other reward. So we can ignore that. And the next state completely depends on which action we're taking. So we have two options. We have S probability that we go to S1 and we get reward 0, given that we are in S0 and we take the action left, times this. In this case, the reward is 0. Okay, we have to specify gamma. Let's say gamma is 0.7. 0.7 times, and whatever the value will be in S1. I don't need this bracket. Plus, and this plus is from this sum. The other possible option is that I have I stay in S0, I get reward 0, and I am making the action. I think I should have said right here and left here times 0.7, and then value S0. Okay, so why is this like this? It's because basically the point is that in this sum, every probability is always 0 except for these two. And this is what we see here, because S1, so we have S0 here. You can see in this list, which ends here, the only ones where we have S0 are these two. And so all the other ones where we have S0 is 0. So that's why in the sum, these are the only ones that are left. So we get this. And this probability is 1. And this probability is also 1. So we're actually being simplified to a very simple thing. Oh, even more. Here, the action is already fixed. So actually, this should have been, yeah, so I actually already pushed up in this sum. So I already summed up over the action. Okay. So this is this. So to be more precise, if I fix an action, I fix a reward and I fix the next state, the only possibility when this is 1 and not 0 is given by the corresponding row in this list. Let's do the same for the other state. So again, we have 50-50 probability which action we take. And if I fix that I'm going to the left, and I fix that the next state is S0, then yeah, so it's actually more convenient to bring this sum out. So I fix my action is left, and my next state is 0, S0. So that's this row. So with this row, this is 0.8. The reward is now 1. So I have 1 plus 0.7 times the value at S0 plus I don't need this bracket. plus again 0.5 and again left, but a different. What's the probability that with the action left I stay in S1? Well, it's this. And so that's probability 0.2. That's this one. Then reward in this case is 0. And 0.7 times, and I'm staying, so I add value of this current state. And okay, so this whole thing was if I go left. So actually, well, this 0.5 is the same as this one. I just opened the brackets already. And then the other option is I go right. And if I go right, it's for sure I lose points and for sure I stay in the same place. So 0.5 times 1, which is for sure. And reward is -1. So -1 plus 0.7 times the same state's value function. If I simplify these equations, which I can, now I don't need this anymore.
Excuse me, in the second one, it says that from state 1 we go to left, and then we will end up in states S0 with the probability of 0.2. I just want to know how to read the second.
This one?
Yeah,
S0, 0.
yeah. No, if I'm in state S1 and I move to the left, I'll be going to state S0 with a
Yes.
0 reward.
That's correct. Sorry, yes, you're right. What I wanted to say is that this is S1. That's what I wanted to say. You're right. Can you please send me an email after the lecture?
Yeah.
Because that's good. That means that we pay attention and we get points. I remove this so that I can simplify this equation. And what time is it? Oh, we're late. Oh, I'm sorry. Oh boy. Okay, so if you don't mind, this is the let me shorthand. This is V0 and this is V1. So V0 equals half times 1 times 0.7 times V1 plus 0.7 times V0. V1 equals 0.5 times 0.8 times 1.7. No,
I think you missed the 0.5 on the top equation.
sorry.
On the top, you should have a 0.5 on the other one as well, right? If you multiply the. No?
There.
Yeah.
Oh, the brackets. You're right. Yeah, right, I forgot to open the brackets. You don't get points. Um. And then, okay. I want to combine everything into one. But maybe it's too ambitious. Okay, so this 0 is 0, so we have 0.5 times 0.2 times 0.7 times V1. And then here we have 0.5 times 0.7 V1 minus 1. Okay, I'm not gonna continue, but you can see that this is just two equations, two variables. These are linear. If I open the brackets here, I get this into the form where this is a matrix, and this is some vector, and V is this vector. So I can express this whole thing like this. And now we can see that it has a solution. So we can solve this by inverting the matrix. And that's how we get the value. That's how we get the value. And it's the same thing with the optimality equation. But with the optimality equation, it's even better because when we solve it, we get actually not just the value, we get the optimal, the best possible value. And it's not absolutely clear that the optimal policy exists, but it does always exist by the proof of that, which is, by the way, not in the books. The books, for some reason, skips it, completely ignores the question that this equation might not have a solution. But it can be proved. And otherwise, you could have potentially a situation that there's one policy which is good here, but bad there, and some other policy which is good here, but bad here, but you cannot find like one policy which is optimal everywhere. But it turns out because of the Markov condition and this way of discounting, it actually always exists. So that's it. Thank you. See you Friday online. And yeah, just send any questions because on Friday we will have questions and Q&A before the exam. The exam is 1 week after next Monday. So yeah.